start with the following polynomial. Notice that it's missing an x squared, so we're going to have to watch this when we do our synthetic division. So to solve polynomials, we have a few rules that we need to look at. We're going to start with Descartes. So if you remember Descartes' rule of sign change, we're looking for changes in sign of the coefficients of each term. So when I look at it for f of x, I noticed that x cubed had a positive 1 in the front. It became negative at -3. And then it doesn't change sign again because our last term is a -2. So we've got a positive and two negatives. So knowing that, Descartes' rule of sign change gives us the following information. If I needed to find out how many positive roots I'm going to have, I just count the changes. In this case, we had only one change. Now, many of my students know about the conjugate pair rule where we start subtracting 2 from the possible roots. But if I subtract 2 here, I don't have enough roots to subtract 2. 1 minus 2 becomes a negative. So our possible positive roots, there's going to be one of them. Now what about negative roots? We need to plug in a negative x to figure out negative roots. And what this is saying is, well, what happens if I have a negative x as one of my roots for this polynomial? So I'm going to go ahead and plug that in to my original equation. And I'm going to simplify. If I've got negative x 3 times multiplied by itself, I'm going to end up with a negative x cubed. If you guys remember in class, odd exponents will leave the x negative, even exponents will make the x positive. Here I've got two negatives multiplied by each other, so I'm going to end up with a positive 3. And then the constant at the end is a -2. So now I'm going to do the sign change again. I start with a negative here. It becomes positive at positive 3. And then it becomes negative at -2. And this gives me the following information. I could have 2 negative roots. Now there was a problem with this because of conjugate pairs. Remember that if I have a 3 plus I need a 3 minus I to cancel them out. So that means if I have 2 negative roots, but one of those happens to be an imaginary root, then that means it has to have a partner. So there might not be any negative roots if I end up having some imaginary ones. So we got to watch out for those. So why do all this work with Descartes' rule of sign change? Descartes' rule of sign change is going to help eliminate some of the work that might come up. If I find one positive root right off the bat, I don't have to keep checking my positive roots because I already found the only possible positive root available. So keep that in mind as we work through the next step. Okay, so now that we've got Descartes' rule of sign change information, I'm going to move on to our rational root test. So my rational root test says this. I'm going to label p and q up here on my function. So p in this case, it always refers to our coefficients. P is our last term. And in this situation, it is a -2. Q is the first term's coefficient, and that is a +1. And if you remember from class, our rational root test requires us to find the factors of p and q and turn them into fractions with p in the numerator and q in the denominator. So why bother? Rational root test helps us figure out what roots would be possible roots to test and factor out our original function. So if you remember, we can have plus or minuses. I might have a positive 1 times a negative 2, or I might have a negative 1 times a positive 2. And in both instances, I would get negative 2 as a result. So these are my factors, and notice they both have a plus and minus. Looking at the bottom one, I could have positive 1 times positive 1, or I could have negative 1 times negative 1. And in both situations, again, I would get a 1 as a result. So now that I have these possibilities for P and Q, I can create fractions from them. I've got a plus or minus 1 over 1 and a plus or minus 2 over 1. Now that's a little weird to look at as fractions, so let's go ahead and simplify. Our possible roots that we will have to test are plus or minus 1 and plus or minus 2. So again, our rational root test gives us possible rational roots to test to create factors for our original polynomial. Now it's time to test these roots and see which ones are factors of our original function. And to do that, we're going to use synthetic division. We could use polynomial division here, but since polynomial division often gets a little tricky, synthetic division is a nice systematic shortcut to finding out if roots are factors of a polynomial. Now when we're using synthetic division, we're looking at the coefficients of our original function, but we had a problem with our original function. And that problem was that it was missing an x squared term. But that's not a big deal. We can make an x squared term without ruining or changing the original polynomial. And to do that, I'm using 0 as a placeholder. Notice that whatever x squared is, it really wouldn't matter because the 0 would get rid of it. So I'm using 0 as a placeholder so that when I work through my synthetic division, I don't forget the place for the x squared term. So now we're going to go through synthetic division, and we ran over this in class. I make a small box for my factors that I'm going to test, and I'm going to write the coefficients in the front. 1, 0, -3, and -2. And I'm going to carefully multiply and add, and I want this to be a 0. If this comes out a 0, remember, that means we found a good factor. So, let's test a number. We're going to test a number 1 and see what happens. So our first one, if you remember, just drops down. Can't do much with that because there's nothing to add there. Remember, the numbers above the line we're adding. And the little number in the box is multiplying to this bottom stuff. So 1 times 1 is 1. And again, I'm adding the numbers above the line. So 0 plus 1 is 1. A lot of 1s happening here. Now I'm going to multiply my result again by the little number in the box. 1 times 1 is 1. Then I'm going to add -3 plus 1. It's a -2. Multiply my result by the number in the box. -2 times 1, that's -2. And then I'm going to add up the numbers above the line. That gives me a -4. So that didn't work. We did not end up with a 0, which means that number did not divide nicely into the original polynomial. We had a remainder. And when we have remainders, it means that these numbers were not factors. So let's try another one. Let's try negative 1 because that's the next one on my list. I had a positive 1 and I had a negative 1. So now we're going to try a negative 1. And again, we're aiming for 0 here because it means there was no remainder. So I'm going to drop my 1 down again because 1 plus nothing is 1. My result, I will multiply by negative 1. I'll add these up. 0 minus 1 is negative 1. Multiply my result. Negative 1 times negative 1 is a positive 1. I'm going to add these two. Negative 3 plus 1 is a negative 2. And then I'm going to multiply my result by the little number in the box. Negative 2 times negative 1 is a positive 2. Finally, I'm going to add up these two numbers, and luckily we get a 0 here, which means that negative 1 is a 0 of our function. And if this is a 0, or a root, then that means that our factor is an x plus 1. That's by our zero product property. So don't forget that step, or make sure that if it's a negative 1 root, then it's a positive 1 in the factor. Now our remainder theorem tells us this. If this was an x cubed function, and we just took out a factor x, then what's left is an x squared function. So again, we had an x cubed function, we took out an x, and now we've got an x squared function. So again, our remainder theorem tells us that if we took out a factor, our leftover is going to look like this. 1x squared, notice I dropped the 1, it's unnecessary, negative 1x minus 2. That's our leftover. So our remainder theorem gave us the following information. And when I go back to my original function, it tells us this. My original function is equal to the little part I factored out and the remainder that I learned from my remainder theorem. Now we're not finished because this isn't completely factored. We've still got an x squared happening here, and we want a bunch of binomials that have x's in them. That way we can graph. So I need to continue to factor this. And I could keep doing synthetic division. I could continue to check my rational roots, test them using synthetic division. But luckily, Algebra 2 taught us a really nice option for quadratic polynomials. We could try a Punnett square, or we can use our quadratic formula. So Punnett square is an option, or quadratic formula to find the remaining zeros or roots. Now I happen to know that the Punnett square would work for this one because I made this problem. But on a test or during homework or during other times where you're critically thinking, you use the method that you feel is going to serve you best. So I'm going to go ahead and use our Punnett square, and I'm going to run through this kind of quickly because you should be familiar with your Punnett squares already. Negative 2, and I have a b term of negative 1. I believe you also like to use the diamond method where we have a times c and b. So I've got a negative 2 and a negative 1, and the only way I'm getting that is a negative 2 and a 1 there. So I can plug those in to my Punnett square, or my generic rectangle as we've started calling them, and I can fill in the edges of my box and I'll find that it factors really, really nicely. And so now I'm done factoring. Now I can rewrite my original polynomial as the three factors that we've carefully taken out bit by bit. The factor that we got using synthetic division, and then the two factors that I got using my generic rectangle. Now I'm finished factoring because I have binomials that don't have exponents inside the parentheses and are nicely factored out and ready to be graphed. Okay, so before we graph, there's a few things we want to point out. First, my y-intercept. I could plug in 0 to my factored form and multiply. Or I can remember that standard form holds our y-intercept already, right there at the end, our constant, -2. Another thing that's going to help us make a nice picture is here. I have two factors that look the same, which means I've got an x plus 1 squared. Now this is okay. I haven't changed the nice factored form because the exponent's on the outside of the parentheses, not like before when it was inside. So this is good. And then don't forget your x minus 2. We can't leave the x minus 2 behind. And this is an important step because if you remember from previous lessons, exponents that are even mean that our graph will touch at that root. So it's going to touch the x-axis, while the x minus 2 having this 1 in the exponent, we don't normally write that, but we'll write it just to look at today. Since the 1 is odd, this tells us that we're going to cross the x-axis at x equals +2. Now remember, our roots are opposite from the binomials because of the zero product property. And this touch and cross information we are gathering from the multiplicity. More vocabulary for your test. So now that I've got all this information, I can grab a graph and I can graph these things. And again, I'm going to make little notes to myself so I can graph it as accurately as possible. These pictures are to give us good information, especially when word problems are involved. So, we have a root at x equals -1, and we've got a root at x equals 2, and our y-intercept is at -2. Another thing we might like to point out is that the coefficient here of our function is a +1, and it's cubic, so that means its shape's going to look something like this. It's a positive cubic function. So when I come down here to graph, I'm going to make some notes to myself that we're going to touch the -1 and then cross at 2. And now I can carefully graph this. Now we don't have a whole lot of information about the minimum here. This has to be a maximum because it just touches the x-axis. And we just know that the shape's going to look something like that. But remember, if with quadratics, having the x-intercepts and the y-intercepts was already a lot of information, and it's going to continue to be that way for our polynomials in this unit.